So our final speaker today is Dave Kelf from Breker Verification Systems, where he's Chief Executive Officer. He's going to be speaking about SoC verification and Synthesizable VerificationOS. Dave is a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for the co-design system Verilog, Novas, Verdi, and others. Today he serves as the CEO of Breker, the leader in test suite synthesis solutions, has a solid engineering background and performed many ASIC designs and holds a microelectronics MSc from Brunel University. And he's over in the East Coast of the USA. So over to you, please, Dave.
Thank you, Mike. Great. Yeah, so what we would like to talk about is a workshop that was presented at DVCon 21 this time last year, which was discussing the idea of a synthesizable verification OS. This workshop, the actual whole video of it, which is about an hour long, is available on the website at this link, and this presentation will be up on Mike's site, so you can easily get a hold of it. The workshop was presented by Adnan Hamid, who is the CTO of Breker, and also Mike Chin, who's a principal engineer at Intel, who's worked with us quite a bit on this concept. So, and where this comes from is a sense, and actually you heard this from Nick's presentation and some other people as well here, this idea that the verification of SoC cannot be just simply accomplished at block level alone. That today, at the SoC level, we have infrastructure complexity, as we would term it, which is, of course, mainly cache and system coherency, security, interconnect, and so on. There's also functionality that now needs to be tested at the SoC level across hardware and software, and also profiling and trying to ensure that the SoCs behave as expected is also becoming much more critical. And then on top of that, we're now seeing firmware verification being performed at a much earlier level than, or earlier time than was done previously. So it means that we need to take a hard look at SoC verification, and we've been doing this with a number of companies, including Intel. Since Mike was good enough to sort of publicly talk about this, I'm allowed to mention that you know, he has been working with us on this. Basically, if you look at Mike's challenges, and these are the ones he presented in the workshop, a lot of the earlier stuff is fairly obvious, you know, time to market and quality. But when it came down to some of the more specific challenges, scaling across both verification platforms and from IP to SoC, the coverage requirements of SoC, which are very different, of course, to blocks, where you're starting to look at how concurrent tests operate, and also, you know, how bottlenecks can occur in an SoC. And then, in particular for his problems, talking the same language as you know, other companies that they're working with, looking at problems like power management and so on. So this notion of a verification OS, some kind of layer that allows some of these capabilities, came up, and it's something that we've been looking at privately with a few companies, but are considering in the future of opening this up to the public domain. So what is this thing? So the idea is, if we want to create a set of tests that can be activated across the whole verification process, we need some mechanism to allow us to do this. By producing like an operating system kind of concept underneath test content that provides mapping functions, scheduling, and execution management in all these different areas, we believe there's a lot that can be achieved in terms of shifting left, both test content production, and now we're seeing firmware as well, the reuse of test content, and also the just making test implementation, particularly at the SoC level, a lot more straightforward, and eliminating the repetition that comes with a lot of sort of detailed test work that then has to be redone for coverage and so on. And there's analogies to this, of course. In the software world, we wouldn't dream of writing a piece of application software it wasn't sitting on top of an operating system such as Linux. And the reason is Linux provides a lot of those things that I just mentioned, including you know, mapping functions, as you see here, memory allocation, and so on. And in the verification world, we see the same thing to a certain extent at the UVM level, where it provides some kind of functions like this, but very little at the SoC and for post-silicon diagnostics or even prototyping. So what is it that we need to accomplish in something like this? We believe there's three major sections in a verification OS that be working for verification as opposed to a general Linux-like OS. Firstly, we need some virtualized services that allow tests to be constructed that map to virtual functions, and these then map to specific functions for the different kinds of the process. Secondly, we need to be able to schedule tests and resources, and at the SoC level, this means scheduling multiple tests concurrently. And thirdly, managing the execution of those tests and synchronizing between processor code and I/O transactions and so on. From a mapping point of view, this is the set that we came up with. And this matches to a certain extent the portable stimulus realization work that's been done in PSS 2.0. However, it goes well beyond that in things like interrupt management, transactions, and so on. And we believe this provides a good set of services that allows SoC tests to be created and mapped onto an SoC very effectively. And I can show you a couple of examples of this. In portable stimulus, there is now the idea of memory allocation, which of course is very key for SoC type testing. What we're able to do here is leverage the PSS type code structures and then map those into the verification OS capability to actually do memory allocation on the design. And I'm sorry, I'm rushing through this a little fast. It was a 1-hour workshop, which I've condensed to 15 minutes for this. But like I said, if you're interested, feel free to look at the whole thing. The other area, a critical area, of course, is register definitions, which change depending on the phase of the verification process you're in. And at the SoC level, of course, this is set up for both firmware and for testing purposes. We're sticking with the UVM register mechanisms and using the RAL layer essentially to map onto this. And we found this works pretty well, as you'd imagine, from the UVM level, but right through SoC and beyond. The second part of the verification OS is the notion of test scheduling, and this is a really key part which occurs much more at the SoC level than we see at the block level, of course. So if you imagine you've got an SoC like this, one way of testing this is to serially line up, one test which runs through these blocks and then a second test. However, at the SoC level, what we need to be able to do is use fully leverage multiple threads, multiple processes, and so on. So the kind of testing you need to do looks more like this, where you're running blocks concurrently across these different threads. And you notice here that this has to be managed given the resources of the design, because you can't, if you've got one particular I/O block like I/O1 here, the purple one, you can't reuse that twice in the same test. So managing and scheduling these resources, much like a regular operating system might schedule different software functions, is very, very important. And if you can do this, then you're able to start seriously profiling the whole SoC, understanding the different buses, bus structures, bottlenecks that might occur in the memory subsystems, and so on and so on. And as I mentioned, of course, it's not enough just to execute operations. We have to do things like allocate memory and then use that memory to store and retrieve data as you're running through this kind of system. So any kind of operating system has to have this kind of capability. Otherwise, the folks working the tests has to do this for themselves. So we can save a lot of time by including the capability in a verification OS like this. The third thing is execution management. A verification OS has to manage multiple different kinds of tests that are operating together. C tests operating on a CPU have to be synchronized with transactions operating on the I/O, and indeed backdoor memory access and other things like that as well. On top of that, coverage analysis and coverage cataloging needs to be handled as well, plus debug and profiling. And debug and profiling tends to be different at the SoC level, of course. What we're doing here is looking for tests and the amount of time a test will take to occur, and if it's using up some resource on the SoC for too long, how that impacts other tests and so on. So that, and of course, the bugs that can occur can happen because of those kinds of activities. So debug has to be extended from straightforward functional errors to performance errors and so on inside the SoC. So how does this really play in the real world? Well, at the SoC level, and the work we've been doing with Mike and others, what we've seen is that we can use this to map tests onto different levels of SoC completeness, if you like. So subsystems right up to CPUs and even operating firmware on those systems as well. It provides an ability to perform coverage analysis up front before you execute the test, which helps with emulation. And it allows a lot of reuse. So we can set up apps for such activities such as cache coherency, system coherency, power management, security, and some of the other things that you heard mentioned previously, and make those very reusable and very packaged, so you don't have to reconfigure the tests and recode them for every time you move it to a different kind of design. It also allows for firmware verification, even at a fairly early stage where there may be no processor in the system. The VerificationOS layer can basically handle all those activities that the firmware would require, such as register access, memory allocation, and so on. So this is something now which is which is becoming very interesting, I think, and it does allow this kind of shift left notion for both tests and for firmware. And it allows some advantages for UVM as well, because now what we're able to do is provide a higher level set of tests that can work with the UVM environment and then be easily ported to the SoC area and used on emulation, which are two issues that obviously we would like to see, I think, from the block level type verification process. The mechanics of this at the UVM level shows up nicely how the VerificationOS would take tests and map them onto a UVM type environment. And here we can just basically set the environment up and by flicking a plus arg here, allow the sequencing of the high level tests through the VerificationOS onto a UVM environment. And it works well, of course, for prototyping too. So just to summarize, this was a complete workshop. We were showing how to leverage and use this VerificationOS. This is something we're looking at in the future of bringing into the public domain. We think it satisfies a lot of issues at the SoC level, and we're working with a number of companies on really exploring this and seeing how effective it can be and how it can work with different various environments. Thank you, Mike.
Thank you, Dave. We do have one question. How to identify the register allocation while running a C code in the OS?
How to identify
the register allocation whilst running C code in the OS?
Yeah. So, well, to identify the register allocation, we're allocating registers based on the RAL layer. Using sort of UVM techniques to do that, and then that can just be transported into the VerificationOS and provided as basically an address map that can be used to sort of drive the test from that, if that makes sense.
Yeah, that makes sense. Thank you. And then, is there a proof of concept that people can access to look at this?
Yeah. So on the Breker website, we do have sort of the basic OS. We'd have to set it up a little bit right now. It's not quite as smooth and simple as just being able to provide it and have people look at it. But yes, we do have a proof of concept on the site.
Okay, brilliant. Okay, thank you very much.
Thank you.
Thanks, Dave.